And before being a PhD student at Princeton, he actually spent 1 year with me at Brown. However, we couldn't teach him anything because he knew everything that our department offered. And so we lost him to Princeton, where they could teach him some things that he didn't know yet. So after Princeton, he went on to Harvard, to the Harvard CFA for postdoc, and then he was recruited to the perimeter. So Niayesh has an incredible range of research interests, which span from topics from fundamental theory to hardcore astrophysics. And in fact, he usually tries to combine these topics. In fact, today's talk is about this. He's going to try to show us what we could learn from LIGO events for quantum gravity. So take it away.
Thank you very much, Robert. Thanks, McGill and McGill Space Institute for having me. Thank you guys for joining, and especially thank you, Robert. This has been an absolute pleasure. I mean, Robert and I think first met, trying to think, it was probably January of '99 when he visited for a workshop in the Persian Gulf, Kish Island, and that's been I guess more than 21 years ago. Yeah, I think it's been great. I think knowing him and basically going through astrophysics and cosmology alongside him, even though I guess we only overlap at Brown for 1 year, but of course we all followed each other's work, and it's great to be here even virtually at his institute. So, well, welcome everybody. Thank you for making the time and joining this first seminar, this first virtual seminar at the McGill Space Institute. So today, as Robert pointed, I'm going to talk about some eclectic topics, and you can probably say that by the title, On the Edge of the Abyss. So I'm going to tell you what an exciting, incredible, and horrifying place in theoretical physics and astronomy we're standing at, and how exciting, incredible, and horrifying it might be. Well, it's not going to be all of them, but probably one of them. Okay, so one thing that probably this audience doesn't need any introduction of, but something that's amazing sitting down here and looking back, is that we are witnessing a renaissance of relativity. 10 years ago, there wasn't much in the terms of 10 or 15 years ago, there wasn't much happening in terms of cutting edge probes of strong gravity. But since then, we have come a long way. The past 5 years have seen an absolute revolution in our probing of strong gravity regime, in particular black holes, both in terms of detecting gravitational waves from black hole mergers and in terms of mapping black holes. So what used to be a pretty abstract topic for a long time is now becoming cutting edge observational astrophysics, and multi-messenger astronomy and cosmology. It's being attacked from multiple fronts with multiple methodologies and many, many bright young people who are working on. Of course, what started it all was the great discovery by the LIGO collaboration in 2016 of mergers of two stellar mass black holes, rather massive, but rather stellar mass, but still a stellar mass black holes. And of course, what you see here is the fact that both detectors on the two sides of the continental United States, in Washington State and in Louisiana, they both detected the same signal with a small delay. If you correct for that delay, they're essentially the same signals, and they're perfectly matched by prediction from general relativity. So it was the first direct detection of gravitational waves, which there are very few people who doubt it. And it's also the first direct evidence for the presence of black holes, because there's really nothing else that could have made this thing. And of course, the evidence was so overwhelming that just a year later, the Nobel Prize in Physics was awarded to 3 of the pioneers of the LIGO experiment: Barry Barish, Kip Thorne, and Rainer Weiss. And that was basically the birth of gravitational wave astronomy. It's a very there's a very young field of astronomy, but there's a very exciting field where many exciting things are happening. And as evidenced by recent headlines, only a week ago, we heard about the discovery of the greatest black hole that has been, greatest stellar black hole, one that was very surprising by all accounts. And of course, the other big event in the headlines, and this one is probably one of the most famous images ever that has been seen, and you don't even need to write down anything. It was the first direct image, optical image from the neighborhood of a supermassive black hole by Event Horizon Telescope. So again, I'm not going to say anything because you all, and of course, many people beyond this audience also have seen this image. It became famous more than a year ago when this was made. And now that we are probing gravity and strong gravity so well, it kind of brings us to the question of the next step, which is the quantum gravity. And this is something that you immediately recognize after recognizing our amazing advancement in probing astrophysical black holes, is that you are witnessing the merger of these two great pillars of modern physics. So there are rules of quantum mechanics. Here I have some examples on the left: atomic physics, your MacBook, your iPhone, that are all working so well because we understand quantum mechanics so well. So marvels of engineering, of course, but they're all built on our understanding of quantum mechanics. And on the right, you have an amazing success of general relativity, which is basically, in some sense, the most precise theory of nature. And we've detected gravitational waves, we've imaged black holes predicted by relativity, and we have GPS that work thanks to the rules of general relativity. So these are the tools that are both amazingly successful on their own, but can they work together? And as many of you know, if you just look at the special relativity, which was the first emergent relativity without gravity that Einstein came up with. In fact, there is a successful merger of these two. It's known as the quantum field theory, which led to the prediction of antiparticles. Two of the most famous names associated with quantum field theory, at least in contemporary names, are Steven Weinberg, who is one of the creators of electroweak theory, along with Glashow and Salam, won the Nobel Prize in the 70s. And then more recently, Peter Higgs, who predicted, amongst others, predicted Higgs particle, which gives mass to fundamental particles. And in fact, it was detected a few years ago in Large Hadron Collider. So they both, of course, won the Nobel Prize for this. And that's, again, an amazing achievement of relativity plus quantum mechanics, except that this was just a special relativity. If you try to add general relativity, basically the version of relativity that does have gravity in it, then you end up with confusion and I guess discontent, whatever these emojis mean, I'm not exactly sure. And the reason for that is, in fact, all the observables that you could try to calculate within the framework of these two great theories, they become infinite. They basically diverge. And they diverge in powers of energy and with some coefficients that basically there are infinitely many of them. Now, at low energies, you don't have to worry about them, and you can probably have predictive series. But as you go to high enough energies, basic energy is comparable to the Planck energy, which is 10 to the 27 electron volts or 10 to the 8 joules. You could, in fact, convert it to mass. It's around 10 to the minus 5 grams. And you could convert it to temperature. It's 10 to the 31 Kelvin. So these are very high energies for atomic particles or subatomic particles. But if you actually try to make experiments with those energies for a particle, then you cannot make a prediction because you have to understand both of these theories well. And if you try to combine them, you end up with basically with infinitely many parameters. So this is not the predictive theory as it is. So this has led to, of course, the long journey since the basic dawn of these two theories. And they have led us along different paths. which in some sense have been very successful, but in others not so much. We've had lots of ideas and lots of amazing mathematical results, but in terms of experiments, we've had lots of basically hit and misses, or basically mostly misses. So we searched for supersymmetry, we haven't found it, basically no physics beyond the standard model as we know it. And there are some authors, some of my colleagues, who have suggested that we are in crisis mode. And there have been premature celebrations, for example, the evidence for inflation, which kind of turned out to be just due to dust or turned into dust, so to speak. And basically, some may argue, at least one way to think about the situation is that we have been 40 years basically since the prediction of Higgs and the standard model, that we haven't really had any new insight in fundamental physics that have been confirmed experimentally. Now, of course, this is a controversial topic, but one that smart people do argue about. So as we stand right now, on the one hand, with great observational achievements, but on the other hand, with basically theoretical achievement have been so successful that haven't been outdone in the past 40 years, we are kind of standing on the edge of the abyss. In fact, two abysses, I don't know actually what is the plural of abyss, but two of them. So if you're a graduate student who are trying to start working in theoretical physics and you're looking at your prospects, you could look in both ways, on the, across or over the cliffs. On the one hand, you're looking at the particle deserts, this is on the left, from where we observe physics using LHC around 100, hundreds of giga electron volts. And what lies beyond that is quite uncertain. This is this vast ocean or vast desert. You can pick your own metaphor. All the way to either grand unified theories or Planck energy, where there could be many particles or there could be nothing. In fact, there is no prediction for what might be happening here. Of course, there are lots of interesting ideas that abound, but none are guaranteed. So we might be, if you jump on this cliff, you may not be landing anywhere, unfortunately, and you may not, or you may get lucky, and in fact, we discover the next physics beyond the standard model. On the other side is the cliff of quantum gravity, where we are actually seeing black holes or a strong gravity all the way to the edges of black holes. And of course, this is thanks to great advances either in radio astronomy or to gravitational wave detection. But what lies beyond that, which is of course immensely interesting from theoretical perspective, because inside the horizon of the black hole is lies singularity or interesting quantum physics or quantum gravity physics. There is no guarantee that we can see anything beyond those horizons. So there again, there is another abyss. There could be interesting physics lying there inside a black hole, but there is no guarantee that we could see them. And in fact, the skeptic would say that there is no hope we can actually probe quantum gravity by observing black holes. So we are standing at the edge of these two cliffs. And of course, you have to pick your poison. And this is, of course, great inspirational part for graduate students, that things may seem desperate right now and you have to pick this. But in fact, things would hopefully, by the rest of the talk, at the end of the talk, I'm going to convince you that, in fact, there are exciting things that are happening, even though the skeptics may try to convince you otherwise. So let's get to the rest of the talk. So with that introduction, I'm going to tell you about two exciting possibilities that could tell us about what lies beyond this abyss of theoretical physics, either beyond the horizon of the black holes or beyond the particle desert, which, so this is in fact the particle desert that some people refer to, that may or may not exist. So I'm going to start with echoes from the abyss, which is our program. We've been engaging for the past 3 or 4 years as to understand quantum physics of black hole horizons. But before we get there, let's just talk a little bit about black holes. Now, most of you know this, but for the students amongst us, so Einstein showed that gravity is geometry of space-time. So gravity is not really a force, despite what you learn in your undergraduate physics, but rather just simply geometry. And what happens is inside the horizons of black holes, which are solutions to the Einstein theory of gravity, space-time is so curved that even light cannot get out. And instead, if you pass this surface, which is not a very sharp surface, it's not something you notice when we pass it. But if you do pass this surface, then basically, according to the laws of gravity, you cannot get out. But the only possible fate that you could have is to be crushed by a singularity, which is not really a point in a space, but rather an event in a space-time. But basically, what horizon means is that if is a place in a space-time, but if you're inside of it, the only fate that you could have is being crushed by the singularity. If you're outside of it, you have an option. You could still fall into the black hole. You could get out, but inside of it, you don't really have an option. An event horizon in relativity are things that generically emerge through astrophysical processes or more exotic processes. They are global structures, so they don't necessarily have any local significance, but they separate basically points with singular fates from points with non-singular fates. And in classical relativity, local observers don't experience any drama as they enter the horizon. So if you have a big enough black hole and you cross it, it's not something that you would notice in classical relativity. However, what happened since the earlier predictions of relativity was, in fact, well, classical black holes, also another property is that they don't have any hair. So this is a technical term, which means that basically all the properties of black holes disappear over time, and everything that you can see from outside is their mass, their spin and charge, which is tiny for astrophysical black holes. So astrophysical black holes, after all is said and done, they just have really two properties. Like things fall into them, and then nothing can get out. However, in the 70s, Hawking, Unruh, and others showed that quantum mechanics, in fact, makes this a bit different, and quantum black holes have a temperature. And in fact, they would eventually evaporate should they be left alone in vacuum. Of course, real black holes are never in vacuum because there's still always plasma around them. But you could imagine ideal situations or thought experiments where you have black holes in vacuum. And then, in fact, the calculations of Hawking and Unruh and others shows that they should evaporate because, in fact, they have a temperature. Now, this has been a very productive theoretical playground for the past 4 centuries, in fact, since the 70s. And in particular, I think one of the last big wave in this is so-called firewall wave or firewall trend, which is in 2012, Almeri, Marl, Polchinski, and Solly, they argued that Hawking evaporation and classical horizons cannot be consistent together in the context of quantum mechanics. So if you believe in quantum mechanics and you believe in this picture of horizons being the same as this, basically smooth places in a space, they claim that there is no consistency there. And they had a solution for this they call firewalls, basically that the standard laws of physics should break down as you cross the horizon of the black hole. Now, there could be other solutions, but this is the one that they claim is most conservative one. And another implication of this is that if they're right, then the observers burn up, that means that they lose their information as they cross the horizon. In fact, the horizon should be replaced by the firewalls. Now, of course, nobody knows exactly what these firewalls are, but the idea is that classical physics, as we know it, should break down within a small microscopic distance of the black hole horizons. So this led to an interesting proposal, which we kind of build up on. There was this proposal was, in fact, due to Cardoso and collaborators. Only a few weeks after the first gravitational wave event was announced. So they suggested that if you have something like a firewall that sits near the horizon of the black hole, in fact, what it does lead to is it does give you the same signal as you expect from general relativity for the inspiral, merger, and ring down, but there would be delayed signals, the so-called echoes, that could be significantly later than the main gravitational wave event, and they would be repeating. So this is what we call echoes from the abyss, and you can in fact predict how, if the firewalls are a Planck length away from the horizon, you can predict how long it takes. So for the first event that was discovered is around 0.3 seconds. So you don't see it in this plot, but it's kind of, I guess these are, in fact, yeah, you don't see any scale here. I forgot to put it, but it will be somewhere down here if you do have echoes. I'm going to show another plot that shows that. And it turns out it's a time that's long, but only logarithmically long, the time scale for echoes, because basically it takes logarithmic amount of time to reach within the Planck length of the horizon and get out. So this is, on the top, you see a simulation of merger of two black holes, which I guess are slightly different masses. You could see that from asymmetry, and as they get closer, the frequency goes up. And then at some point, the horizons merge, and then you have just one final black hole. So that was just kind of this signal that you see here. Now, we don't have a simulation of black holes that emit echoes. In fact, that's an open problem that we are currently working on. But the proposal is that actually after this merger happened, if you wait for a while, basically around 0.3 seconds, then you're going to see these echoes. And this is kind of roughly the kind of signal that we're looking for. And in fact, this should repeat roughly every 0.3 seconds, although the exact time depends on the event that you're looking at. So that's the proposal. And that's really a way to test firewalls if they are really observable. Now, just because they are there doesn't mean that we should see them. But in fact, with my PhD student who's just finishing up and postdoc at Perimeter, Naritaka Oshita, in fact, we showed, I think, based on some very generic arguments, in fact, 3 different lines of arguments that are independent based on fluctuation dissipation theorem, based on thermodynamic detail balance, and based on assumption of CP symmetry of the final black hole state. We showed that basically you expect echoes based on a stimulating Hawking radiation, and then you get a universal reflectivity, which is in fact given by a Boltzmann factor. So that actually, what that means is that at high frequencies, black hole horizons are in fact black, as we see and we expect. But as the frequencies or energies become comparable to the Hawking frequency, which in fact does happen for gravitational waves, then you expect order 1 reflectivity of the horizons. And the way to think about it is if you just think about from the point of view of quantum mechanics, if you think about black hole is some complex excited state of gravitons or matter, if you want, is like a very big atom. And what Hawking radiation is just basically decay of this excited state as this excited state, like an highly excited atom or molecule, as it decays, it kind of keeps emitting photons. And Hawking radiation is believed by most people to be something like that. You have an excited state of quantum gravity, which as it kind of goes down in a state, it emits more and more gravitons or gravitational waves. Or it could be emitting photons or all sorts of things. Now, what happens is that, in fact, what our calculation shows, based on those arguments that I showed you, is if you, in fact, put this black hole in some background of gravitational waves instead of just in vacuum, as Hawking was doing, if you just put them in some background of gravitational waves, these gravitational waves could stimulate Hawking radiation. And that would lead to what we call echoes with the Boltzmann reflectivity that I suggest. So at high frequencies, you would get very little effect, but at high frequencies, at high frequencies, you get very little effect, but at low frequencies, you can get significant stimulated Hawking radiation. In fact, another way to think about these echoes is that echoes to the LIGO is similar to the Higgs to Large Hadron Collider, at least in terms of their motivation. They're both based on the assumption that quantum mechanics is valid. They assume locality. The one place where they differ is that for the Higgs, you have to assume gauge symmetry basically, the reason you need the Higgs is to preserve the gauge symmetry of a standard model. On the left-hand side, for the reason you want echoes is based on the holographic principle, which comes from the equivalence principle and a combination of that and quantum mechanics. So if you really want quantum mechanics to be safe everywhere, then at least there is motivation that you should be looking for LIGO for the same reason that you were looking for the Higgs particle. Although this could be unarguable, but I like to suggest that as this from my point of view is that these are similar exercises. Another interesting coincidence that it's kind of more on the theory side is some of you may have heard about this term fast scramblers or scrambling time. This was a proposal by Sekino and Susskind where they kind of, they were bringing the idea that basically bringing, marrying the ideas of quantum computation and black holes or geometry. This is like one of the pioneering works in it. And one of the proposals was that black holes are basically objects that have the maximal speed or efficiency in scrambling information. It means that if you kind of, you have an object and then you throw a qubit of information in it, the fastest that it can spread across all the degrees of freedom is the one that's being done by the black hole. And in fact, there's a time scale which is proportional to the logarithm of the number of degrees of freedom. This is known as the scrambling time. And in fact, we showed that my student, Krishan Saraswat at Perimeter showed that the fastest scrambling time that was proposed first by Sekino and Susskind in all the contexts that we look at is in fact equivalent to the echo time that we find in the gravitational context. So it's an interesting coincidence, and we kind of went through all the literature, and it was a very interesting coincidence, even though these are very different places that it come from. Fast scrambling came from quantum information and holography, and echoes came from gravitational wave astronomy. And we've been kind of working more further on this. We have a proposal that in fact there's a way to holographically understand echoes by studying the non-perturbative evolution of out-of-time order correlators. So this is an ongoing work. And also from another proposal, the so-called Kerr CFT proposal. And this is something that should be coming out any day. In fact, this is inspired by one of the papers that came out of McGill by Alejandra Castro, who is a graduate student there, a PhD student, Alex Maloney. And they suggested that, in fact, they showed the correspondence between gravitational wave propagation around Kerr black holes and 1+1 dimensional conformal field theories. And in fact, we showed that the fact that you have a conformal field theory in a circle naturally leads to the idea of echoes, because signals that propagate around a circle, they always come back, but maybe even with some damping. So we could, in fact, we showed that in the context of this Kerr CFT, you could exactly get this Boltzmann reflectivity or Boltzmann echoes. And here is like the absorption. Here's an example of absorption cross-section as a function of frequency, where you see this resonance behavior, which is characteristic of a characteristic we see from the echoes. So let me see. I would like to ask: are there questions here that I should maybe answer at this point? Okay, so I hear abysses is a plural, and a Scrabble. Good to know for a Scrabble. Okay, and okay. Also lead to echoes. So that's the next. So Robert asked whether fuzzballs could lead to echoes, and I think the answer is yes. Although it is debatable. Depends on. I think it somewhat depends on who you ask. But I think based on our calculations, they should. Okay. So another issue that another interesting perspective on this issue of quantum black holes is what we call quantum black hole seismology. And this is work again with Naritaka, who's at PI, and Daiichi Suna, who's part of a member of LIGO collaboration at the University of Tokyo. And you could look up these, and they have two papers that are now both in Physical Review D and this. And the main idea here is that you could basically use seismology the same way that we can explore the inner core of Earth or stars by looking at their spectra. You could do the same thing with quantum black holes. And we contrast this from a spectroscopy with a spectroscopy where people have been doing basically for black holes for the past few years, what it's been talking about, where you probe the outer parts of an atom or the outer states of an atom. So that's called black hole spectroscopy. And then kind of that probes around the photon ring, which is around 3 times the mass of the black hole. But the seismology is the idea that you could in fact probe the inner part, the quantum structure of the black hole. And in fact, these are some examples that we did. So a quantum black holes could have non-trivial properties. They could have a reflectivity law. They could have different harmonics that are excited, and they could have different temperatures. And these are examples of what would happen. So if you have a constant reflectivity, so what I'm showing here is the power spectrum of gravitational waves as a function of frequencies. And these will be gravitational waves that will be emitted upon merger of two black holes. And what you see some kind of underlying a smooth curve here, but that's what you expect from general relativity, something that looks like this, in fact. But these wiggles that you see is in fact what you get from quantum black holes because of the reflectivity of the horizon. So here, if as you see as you change the spin, this peak frequency changes. The peak frequency is in fact close to the horizon frequency, and sorry, it's close to the quasi-normal mode frequency. But as you change the spin, what you see is that this structure changes because this quasi-normal mode frequency changes, but this structure also changes. If you change the reflectivity law from constant reflectivity to Boltzmann reflectivity, you see that the ratio of the peaks change. So here, all the peaks look the same, but if you switch to Boltzmann reflectivity, which is what I introduced to you, so it's basically if at high frequencies you have zero reflection, at low frequencies you have large reflection. And it turns out that maximum reflection is when the frequency matches the horizon frequency. So you get a peak around that. Basically, the maximum reflection happens when the frequency in the rest frame of the rotating black hole is zero. And that's what leads to this peak that you see here. But that, in fact, depends on the harmonic. So you could actually infer which harmonic is most excited, depending on which whether you see a peak at finite frequency or at zero frequency. And so there are various aspects that I'm not going to show you a lot of them, but you could in fact probe all of these using black hole seismology, which is basically by studying all the resonances that appear in the spectrum of a quantum black hole. Basically, you observe gravitational wave emission from binary black hole mergers and look at its frequency spectrum. And if you have a high enough sensitivity, you can see in principle these structures if they're there. So you could see now. Can we see this in the data? Now that's in fact a controversial topic. So two of the papers that I've done on this are listed here in terms of observations. They are both by led by Jahed Abedi. So it's that short answer. You should stay tuned. So Jahed has led this effort for both for different LIGO events. And it seems that there is some evidence, which is from tentative to more decisive, from 2.5 to 4.2 sigma. But it turns out that not everybody sees this. Now, I should say that the second author in this, Hannah Dykar, used to be a student in McGill. Some of you know her. In fact, she worked with Daryl and then with others as well at McGill. And you may not know her. Not all of them may not know her, but you probably know her mother, who won the Nobel Prize after we worked on this. She is in fact Donna is a colleague of mine at Waterloo as well. And after our work was done, that was back in 2016. In fact, other people saw the same signal. This is one from the members of the LIGO collaboration. They were just looking at using this coherent wave burst method, which is in fact, this is the method that was used to detect this most recent gravitational wave event. Because this is a very freak event that nobody was expected. And the standard searchers weren't looking for this, but this coherent wave burst method is one that looks for flukes in the data that are localized in frequency and time. And in fact, they see two events a bit after two kind of, well, post-merger events around 0.2 and 0.1 second after these two events. And it turns out those are exactly what we predicted in our original paper for these two events. Of course, this is called LVT back then. Now it's called GW, but it's the same number, 15, 10, 12. So it's an interesting prediction that this just comes from the prediction. These numbers come from putting firewalls within the Planck ring of the horizon. and it just turns out that these two events, these two black hole events see the same thing at the exactly when we predicted. Now, why the other events, other LIGO events don't show this, that's the good question. And we don't exactly know why some of them show it and some of them don't. But the timing is in fact interesting. And if you want to read more about the controversy around echoes and who sees it and who doesn't see it and why, you could look at our review article. And you had actually held 2 conferences at PI that you could watch all the talks on Pearsa, one in 2017 and another in 2020. And finally, I guess these echoes were predicted by Simon and Garfunkel and in their timeless song, Hello Darkness, my old friend. You can read the rest, but so there is silent raindrops that fall and then cause echoes in the bells of silence. Of course, they were talking about black hole echoes. I'm pretty sure of that. Okay, so that's the end of the first part of the talk. So before I move on to the next part about the mystery noise from LIGO, I want to interrupt. I want to stop and ask whether any questions. So I see Adrian, Caitlin, and everyone does the reported confidence of the excess observed in the take into account the Lucas-Spur effect. That's right. So the Lucas-Spur effect is indeed the primary question, and in fact, all of these estimates account for the Lucas-Spur effect. But of course, there are 2 types of Lucas-Spur effect. Individual groups have their own Lucas-Spur effect, but there are different groups who are doing their different searches. And some groups find it and other groups don't find it. And different groups have different methodologies. Now, whether it's just because some groups get lucky and others don't, or whether just some people are more careful than others, that's really the gist of the question. So in fact, if you're interested, I can come back to the end of the talk about the difference in methodologies. There are basically half of the searches find something and another half don't find anything. And it really depends on which method you use and I guess which group does it. Okay, so if there's no questions, let's see. If you were to conjure up your dream system for which it's easiest to see the echoes, what would it look like in terms of mass ratios of spins? That's a good question. And actually, that's one that we don't know the answer to. What is the perfect system that could give you the echoes? Because we don't really know what sets the initial conditions. So this is a similar problem in seismology, because you could tell when there are earthquakes what modes should be excited, but you cannot predict when there will be earthquakes or how big the earthquakes will be. And it's kind of the same problem with echoes, is that we don't actually have a nonlinear model for these firewalls. If we do have that, then we could predict what kind of systems would have louder echoes and which would have quieter echoes. There is some weak empirical evidence that the systems with a smaller mass ratio, basically if you have a big black hole and a small black hole, the echoes are more detectable, but it's not clear whether this is something intrinsic to those events or it's more of a systematic, more an observational selection effect. So it's an excellent question. It's one that I'd love to know the answer to. What's clear is that, of course, the louder the event is and the smaller the detector noise, the easier it will be to detect these if they are there. But exactly how they look like, we don't exactly know. So we can predict the frequencies in the linear theory, but the amplitudes are harder to predict. At least more model dependent. Okay, so if there are no other questions for now, I can move on to the second part, which is going to be shorter. So now I'm going to turn my focus from what lies beyond the horizon of the black hole to what lies beyond the desert or particle desert, which is basically this term that people have, or particle physicists have, for what lies beyond the standard model of particle physics. Should we expect to see supersymmetry beyond the standard model of particles, maybe dark matter, maybe strings or extra dimensions, or maybe nothing all the way up to the Planck scale? So that's the, sorry, let me just, I think, Julia, can you be more quiet, please? Okay, thank you. Okay, so let's talk about the mystery noise from the desert. So what's this about? Probably most of you or many of you have heard about the cosmological constant problem. Now, why is the quantum vacuum made out of heavy particles so light? Now, we can measure now, thanks to the detection of cosmic acceleration, we can measure the density of the vacuum, which is, I mean, if you write it, compute it exactly in SI units, it's 7.1 plus or minus 0.9 times 10 to the minus 27 kilograms per meter cube. It's a tiny, tiny density, but it's one that we can now detect, at least on very large scales, thanks to great advances in observational cosmology. Now, if you wonder whether we have a prediction for this from quantum mechanics, then, I mean, probably most of you know this, but it's never really ceases to amaze me to see how big of a discrepancy there is. If you take the standard model of particle physics and compute how much energy there is to it, you're going to get a number of order 10 to the 33 in these units, which is 60 orders of magnitude bigger than what you observe. And in fact, 61 sigma off from, well, around 60 sigma off. Sorry, 10 to the 60th sigma off, I should say. So it's probably the biggest discrepancy in the history of physics, as some people say. Now, in fact, it turns out that this is a problem that can be solved, at least by hand, rather easily by just subtracting a constant. So in fact, there's an expectation value of the energy momentum tensor that goes as mass scale to the fourth power. And this is something that is predicted, but it's also, all you have to do really just add a constant to your action or to your Lagrangian to get rid of it. And even though it's a big number that's, sorry, I think I'm, okay. So even though this is a big number, it's a big number that is easy to fix by just adding a constant. That's something that I'm not going to talk about today, although I could give another talk on this. But today I'm going to talk about something that's less well known, and but it's equally interesting, and it's the fluctuations in the energy momentum tensor. So even if you subtract the mean of the energy momentum tensor to get rid of the cosmological constant, or to make it as small as you want to fine-tune it, there are still quantum fluctuations around it, because quantum fields are quantum. And you could ask the same reason that basically electron cannot sit on the proton in the hydrogen atom because of the quantum mechanics. The quantum fields cannot sit in their minimum, and they would keep fluctuating. And you could ask what are the fluctuations around the mean, in particular, what are the fluctuations of the energy momentum tensor. And this is a calculation that's been done, and with some technical assumptions, which of course it could be very important, basically requires some analytic continuations. What we find is that for massive fields, in fact, others have done this before us, we find this goes as mass to the 5th power for massive field divided by a square root of k squared, where k is the wave number. So this is an interesting observation, because in fact it tells you that fluctuations can become big at the small k's. And then you may ask, okay, so what happens to gravity if you actually plug it in? And it's a question that unfortunately few people have asked, and everybody has focused on a different part of the problem. So with the postdoc at PI, Nelson, and then, oh, come on. Now I'm forgetting his Nelson's first name, but I guess it's a sign of the time.
It's Elliot.
Elliot Nelson. Sorry, yes, thank you. Yeah, it's okay, with Elliot, because I mean, we worked for 3 years, but I suppose that's what pandemic does to people. Yeah, so with Elliot, we had a couple of papers on this that show this behavior and how it affects gravity, but then others, in particular, Bill Unruh have a few papers on basically asking this question of how these fluctuations of a stress tensor gravitate, and Steve Carlip has a few papers on this. We all kind of look at this from different points of view, and we kind of focus on different problems, different aspects of the problem, and we get different results really, because we try to address this problem differently. Now, from my point of view, I think ours is the most rigorous, because we actually solve all of the Einstein equations. The problem is that it's only perturbative. And I think what Steve Carlip and Bill Unruh and company do, they try to make non-perturbative assertions. But of course, then there's more hand-waving involved. So what we found is that if you try to ask what is the fluctuations of the energy momentum tensor, you find something that if you convert it to a standard SI units, something in fact gets bigger on a smaller scales. So even though it looks like it gets bigger, if you actually convert it to regular units, there would be Fourier transforms involved. And so it's something that on a small scale, you have larger fluctuations, the larger scales, you have a smaller fluctuation. That's not surprising because of course, quantum fields do most of their fluctuations on a small scales. However, the interesting thing is that if you actually plug this into Einstein equation and then solve Einstein equation, you see that fluctuations in distance or in length, which is what LIGO is measuring, in fact grows with distance with length as length to the 5/4. And that part is interesting. And so at either large distances or at small frequencies, these fluctuations become more important. And I was surprised. I mean, nobody actually had noticed this before. And as it turns out, and I discovered this when I was listening to a LIGO talk about a year ago in Valencia. There was a keynote talk by one of the members of LIGO collaboration. And you cannot find this in any of the LIGO papers, but if you go online, they do use this word, the LIGO people, all the time. It's called the mystery noise. And it's the fact that if you actually compute all the sources of noise that you see in LIGO and add them up and then compare it with the noise that you actually see in their detectors, there is a gap between them. So there's a gap between the the purple line and the red line here. So this gap. And there is basically no explanation for this. This is in the LIGO published paper, and I actually could download this data. They were kindly provided this data, so I could actually just look at the square of the differences, or a square root of the square of differences. So basically, look at the subtraction quadratures, and this is the mystery node. So this is the spectrum of the mystery node that probably you have not seen because the LIGO collaboration does not like to publish this. But it is actually, you could get it from their data, as is publicly available. So the spectrum of the mystery noise is this orange, is the purple line here. This is from the first operation. For the third operating run of LIGO, I had to do more sleuthing to get it, but there are actually some public web pages that, thanks to one of the members of LIGO, I actually could dig them up and then again do some digitizing and managed to get the mystery noise for those. And those are the brown line and the black line. And you see that there seems to be this more or less consistent mystery noise. Of course, it does go down. So it seems that they get some of the sources of noise under control, but it's still there. At least big enough that at least some members of the collaboration are worried about it. And interestingly, if I actually add the noise that I was telling you from the fluctuations of the stress tensor of the standard model, you get either this orange line or the green line, depending on whether you include or don't include the top quark. And given that QCD is non-perturbative, it's not exactly clear whether the top quark is being added correctly. But so after top quark, Higgs is the next big particle, which is weakly coupled. So basically, there would be something between the orange line and the green line that's predicted for a standard model from these vacuum fluctuations. And there's no free parameters here. It's just I'm adding up all the particles in a standard model. The difference is that this one includes top, but this one doesn't include top. Now, at low frequencies, there's a nominal control noise that I added, which people from LIGO admit that it's there because of just the way the controls work at very low frequencies. So at low frequencies, this stat dominates, but if you go to high enough frequencies beyond 40 hertz, 30 or 40 hertz, then this mystery noise, there's no explanation for it, basically. And I guess the suggestion is that maybe it's really gravity of the vacuum. And interestingly, yeah, there is no free parameter here. It just happens to match as it is. So if this is really the mystery noise, the origin of the mystery noise, and it cannot be further reduced by getting basically more instrumental effects under control, then it could be due to top quarks, basically vacuum fluctuations. And it suggests that probably a top quark is the heaviest particle that there is in a standard model, or beyond a standard model, because if there were heavier particles, they would dominate this effect. So that's really interesting possibility. And in fact, it reminds you of this other mystery noise that you probably have heard about in your textbook back in the 60s, where Penzias and Wilson were building this great radio detector or radio antenna. And they were seeing this noise that they had no explanation. And eventually it turned out this was in fact a signal from the Big Bang. And as you see, that gave us a map of the Big Bang. From on the left, you see the map, and on the right, you see the power spectrum that we can now use to understand Big Bang much, much better. So the question is that can the gravitational wave mystery noise, the same way that the microwave mystery noise told us about or mapped the Big Bang for us, could the gravitational wave mystery noise, could it map the particle desert the same way that CMB probed the Big Bang? So with that, let me end. So the state of the theoretical physics, quite like the rest of the world, as we know, as we knew 6 months ago, appears to be on the edge of the abyss. This could be horrifying and exciting at the same time. I think there is room for great ideas and great breakthroughs, because all the old ideas and old methods have kind of failed, at least from my point of view. So I don't think young people need to despair necessarily. I think just need more creativity and innovation. And I think at this, for this, as far as this talk is concerned, I think there are two surprising insights that may come from gravitational wave astronomy, which is one of the great achievements of science in the past few years, in past 4 years, I should say. That there could be black hole echoes that can shed light on the quantum nature of black holes and gravity. That was a big surprise, only we found out about it 4 years ago. Around the same time, I think LIGO mystery noise, which is really the noise, not the signal that LIGO has been looking for, could be another interesting avenue to learn about the particle physics and whatever lies beyond, or may not lie beyond the standard model of particle physics. Okay, thank you very much. So I see there are some questions. So I guess, do you guys want to take it up, whoever asked the question, since I'm done talking?
Why don't we unmute and actually do questions verbally? Yeah.
Mm-hmm.
Robert, do you want to moderate?
Okay. So, Jim, do you want to go ahead?
Sure. Hi, Niayesh. Very nice
Hi,
talk.
Jim. Thank you.
Concerning your last point about the heaviest particles, so then you would be ruling out things like heavy right-handed neutrinos that people like for the seesaw mechanism, and also a heavy inflaton, anything beyond the top quark. Is that correct?
So there is a caveat here, which is these are all perturbative calculations. So we basically coupling free particles to gravity. Now, if there are non-perturbative effects that happen somewhere between, I guess, from electroweak all the way, somewhere between electroweak and the very heavy scales, then I cannot really say much about that. So is there a way to mask this effect, basically? So that's something I would be interesting. It seems unlikely to me, but it's possible. And it would be some sort. But what I'm saying is that the perturbative calculation suggests that there cannot be these very heavy particles.
Oh, thank you.
Thank you.
There's actually a related question by Heliotson. Heliotson, do you want to ask it?
Yes. So thank you for the presentation, Yash. It was very interesting.
Thank you.
I noticed that when you talked about the vacuum fluctuations, you wrote that the m that you use for the expectation values of the initial momentum tensor is the same m as the mass of the field.
That's
so why should not be the Planck mass? Why are you using the mass of the field as a cutoff?
That's an excellent question. Of course, if it's the Planck mass, it would be much bigger a scale, and it would be obviously inconsistent with observations. So in another way to think about it is that we are putting an upper limit on M, which is around 200 GeV. So certainly it would rule out Planck mass, and it rules out essentially anything beyond 200 giga-electron volts. I mean, Planck mass is 10 to the 18 or 19 giga-electron volts. But again, the caveat that I said still holds, that if there are non-perturbative effects that somehow mask this, then I don't know. So I mean, in fact, you could think of this as another version of the cosmological constant problem. So that's why I call it the cosmological non-constant problem. So you may think that there is the same way that you solve the cosmological constant problem, you can solve this, except that this one is harder because these are fluctuations of something. So if it's a constant, you can probably add a constant that cancels it. But fluctuations are always positive, at least, I mean, physically, unless they're kind of magic quantum field theory things that, I mean, again, it could be weird things that happen that at least are less intuitive that I don't know about. But the fluctuations all add on top of each other. So it would be harder to cancel it. But again, I'm not ruling it out. It might be possible to do it somehow.
So maybe we can take a different type of question. Vicky, do you want to ask your question?
Well, yes, I was just wondering if first of all, the noise that you report, is that seen in both LIGO detectors? And also, is there any hint of it in the Virgo detector? Right. So Virgo has a much bigger mystery noise. So in fact, I mean, Virgo, if you're familiar, everything is kind of bigger with Virgo. Virgo is, I mean, it's a smaller detector, but also then the noise sources are less under control. So, I mean, it certainly could be some instrumental effect. The problem is this one has been persistent over the years. And I mean, when I talk to instrumentalists, of course, they don't want to talk about it very publicly, but they don't really have a good explanation for what's going on in LIGO. Now, for Virgo, it's much bigger, and it could be because they don't understand their instrument very well. And I'm sorry, perhaps you said it, but is it in the same shape and amplitude in both LIGO detectors? Good question. So I gave you three. I mean, these are the three things that I could find. So the purple is for Livingston, which comes from the published paper of LIGO. They don't show it for Hanford. It's not in their paper. And then the O3, I have both for Hanford and Livingston. And that's, they are both, yes, these are these two. But of course, it's not very surprising that they look similar because they're very similar instruments. So the fact that it's the same, they look similar, that's not very surprising. And the fact that it is smaller than what it used to be back in 01, it probably tells you they understand their instrument a little bit better. The question is that, is there still some persistent noise that cannot be explained by any terrestrial source origin, basically. Okay, thank you. Thank you.
Caitlin, you have a question as well?
Yeah, thanks for the great talk. And that's really interesting about the fluctuations. And I hadn't appreciated that before. So that's really interesting. Mm-hmm. And yeah, especially how it grows larger with larger length scales. So I had kind of a naive question about that, which is whether there could be, any interesting like lensing or microlensing kind of signature that could arise from that.
That's an excellent question. So in fact, we thought about it. Our first paper that we wrote on it, we looked at the effect on the cosmic microwave background, which is basically a type of integrated Sachs-Wolf effect. So I guess it's a kind of lensing effect. And we put some constraints, which was around, I think, 100 TeV, if I remember correctly. But it turns out even more sensitive than that is pulsar timing, which is on, well, pulsar timing, you could measure things much more precisely because, I mean, CMB, you could measure to 1 part in 10 to the 5, but the pulsar timing, you can measure 1 part in 10 to the 15. So that puts even a stronger constraint. But then the LIGO thing was, I mean, that it turns out that we hadn't looked at that. That's the most, basically, the most constraining. So I think that the LIGO constraint dwarfs all the other constraints that we've looked at so far.
Thanks, that's really interesting.
Thank you.
So I had a question about this effect. So about the growing the fact that this change grows as a function of length scale.
That's right, yeah.
So I'm worried about the divergence.
Mm-hmm.
If you let L go to infinity,
Yes.
this would be a problem.
Now, of course, now that's an excellent question. It turns out that where it becomes of order 1 is bigger than the scale of the horizon. So basically, we're doing all the calculations in Minkowski space. But if you try to do this in Friedman, Robertson, Walker, then indeed there is a divergence, but it happens beyond the horizon. But as you are familiar, I mean, even in the standard cosmology, we have a divergence beyond the horizon because we see a red spectrum of fluctuations. So if you go to very larger scales, at some point, deviations from Friedman, Robertson, Walker becomes order 1. And of course, whether it's something to worry about, it's an excellent question. I mean, you and I, during the time I was at Brown, we worried about these order 1 fluctuations that are super horizon. What do they mean? And indeed, this is one of the things that could be interesting, whether it could tell us something about the origin of dark energy or something about the origin of fluctuations. I don't know, but this is certainly something that appears to come out of these calculations, that there is a divergence that happens on super horizontal scales. But how much you trust it is a little bit hard to quantify because this vacuum, we don't necessarily understand it beyond horizon. I mean, we understand the vacuum of particle physics very well in Minkowski space. That's where we do particle physics, right? But on cosmological scales, what is the right vacuum? As you know, it's a more thorny topic. And there could be subtleties associated with that what we assume is the right vacuum may not be the right vacuum on cosmological scales.
Thanks.